My slides and my notes are available to anybody who wants them. My email address is webmaster@redbankhumanist.org. So if you want a copy of my deck, you want to know, what my source was for any particular item, I can get that to you. My next note says jot down the slide number. If you have any questions during my talk, if you could remember what slide I was on when that question came up in your mind, it will help remind you of what your question was, and also it'll allow me to throw the graphic back up, so if and when the projector gets here. And also, don't try to understand everything. Sometimes I'm going to go really deep, and if it goes too deep for you, don't worry about it. Just get the high-level idea, because if you understand the high-level idea, you'll be able to be in the conversation, and that's all that's really important. And after having said that, I got to tell you, this is the simplified version. So as deep as I go, we're just scratching the surface here. So I put together an outline, and the first question is, what is artificial intelligence? And this is really a meaningful question, because there's a lot of buzz out there today about artificial intelligence and what's happening in artificial intelligence, and they keep using that phrase, artificial intelligence, as though everybody knows what that means. And very few people know what that means, or, which leads to the next question, well, how many kinds of artificial intelligence are there? There's not just one. There must be several, at least two, right? I've got friends who exhibit lots of it. And then after you understand that, what is artificial intelligence and how many kinds are there, then what are the implications of artificial intelligence today, next year, the year after that, 20 years out? And should we be preparing for it, or should we just let it happen and wash over us? How should we be thinking about this? So let's start with what is artificial intelligence. And, what comes to mind immediately is, well, if a machine can do it, and we always thought only a human could do it, that's artificial intelligence, because it's a machine simulating the intelligence of a human being, right? Obviously. Unfortunately, throughout the history of artificial intelligence, every time they invent a machine that does something that a machine could never do before, and everybody says, artificial intelligence is here, the scientists all said, well, not really. It was artificial intelligence until we figured out how to fake it. It's not really artificial intelligence, we're just faking it really well. And there's a lot of that going on. And the phrase they use is AI until a computer can do it. And I'll give some examples of how that's rolled out in time. So 3 things are driving AI today, and they're around for a long time. I first started hearing about it back in the 70s, because I was in computer science at the time, and there was a country that they referred to as Japan Incorporated back in those days. Yeah. And Japan Incorporated said that they were going to have artificial intelligence in 20 years, and this was in the 70s. So we should have had it in the 90s, and it didn't happen. And why not? What changed? Why are we expecting it to happen today? Well, 3 things. The first one is cheap parallel processing using GPUs. Okay, welcome to the world of jargon. A GPU is a graphical processing unit, and it was invented by computer scientists to solve a huge problem, which was, how are you going to play a video game if you don't have the computing power to play a video game? That seriously was what drove the invention of a very complex piece of technology. And a graphical processing unit, I'll show you what it looks like. This is why we need that projector. This thing here is a GPU. It's smaller than a postage stamp. It's got 3 billion transistors on it, which is a lot. They're about 20 nanometers in size. They're unbelievably tiny. And there are 512 computers on that chip. And each one is specifically designed to handle graphics on a computer screen. Okay? So you got 512 computers optimized for doing graphics, all running the same code, doing the same thing simultaneously. And when computer scientists were looking for ways to emulate the human brain, they said, gee, the human brain has a bunch of computers running in parallel. What can we possibly use to mimic that? And somebody said, wow, GPUs, that's what that is, right? So let's use that. And then more recently, a companies that were serious about artificial intelligence, like Google, decided that they would build their own version of a GPU, and it looks like this. They call it, this is Google's chip, they call it the Google Tensor Processing Unit. And the reason they call it that is because Tensor is the name of the software they use to do their artificial intelligence. So this is like a graphical processing unit, but it's actually, now they're calling them synaptic processing units because they're emulating brain function rather than graphical function. So they're fine-tuned to do artificial intelligence functions. So there's a chip with hundreds of processors in it, specifically designed to think, or to do something that looks like thinking. And then that would be called artificial intelligence, right? What's this?
Witcher.
Wow. This is high tech. I don't know how to do it.
The button on the...
Yeah.
Is it working?
I don't know. I see a light, but I don't see a dot. That's okay. I'll just point. The second thing that's driving artificial intelligence is big data. Now, why is big data even important? It's important because computers don't learn the way humans learn. If you show a little girl a cat and you say, that's a kitty cat, you know, the next day she might see a dog and say, kitty cat, and you say, no, no, that's a doggy, right? You show her another cat and she'll never make the mistake again. She'll know the difference between a dog and a cat. To do that with a computer, you have to show the computer hundreds of thousands of pictures of cats before it finally gets the difference between a cat and everything else in the world. Because what's the difference between a cat and a windmill? If the windmill has 4 legs holding it up, you know, for a computer, that's a really, really difficult problem. So, where do you get those hundreds of thousands of pictures of cats? Well, you get them off the internet. Because if you want to see pictures of cats, that's where they are. Now, just to give you a feel for how much data there is in the world now, this is 24 petabytes. 24 petabytes. And that's a number that's totally incomprehensible to everybody in the world. Even if you're a mathematician, 24 petabytes means nothing. That's how much data is processed per day by Google. Okay, 24 petabytes of data. So how much is that? Well, if 24 petabytes is equivalent to about 2.4 trillion Webster's unabridged dictionaries. And if Webster's unabridged dictionary is 3 inches thick, that many dictionaries stacked up would go past the sun. Okay? And that's how much data passes through Google every day. So how do you process that much data? How do you make sense out of that much data? Because data is not information until you formulate some way of thinking about it or looking at it or categorizing it or summarizing it, right? Then it turns into information, and then you can take action based on that. If it wasn't for the rise of artificial intelligence, we wouldn't know what to do with all that data. We need AI to make sense out of that. The last thing that's pushing AI today is better algorithms, and that's a complicated thing to say because what the heck's an algorithm? All you know is they're better, right? An algorithm is like a cookbook. It's a recipe for how to do something. So if you're going to balance your checkbook, if you've ever balanced a checkbook, you always do it pretty much the same way, right? So that's your process for doing a checkbook. And if you do the process right, and you follow the steps in the correct order, that's going to get you success at the end of a balanced checkbook, and that's called an algorithm. And I'll give an example of what an algorithm is as we go on. But before I go any deeper, I want to say a word about robots. I told you I would. AI and robots are two different things. Okay, first off, anything that can do anything that even comes close to artificial intelligence is so big, you know, in terms of physical size, it would never fit inside the head of this thing. If you ever saw any of Boston Dynamics robots, the robots that Google has been trying to sell, they have this huge backpack that they walk around with, which makes them really ungainly looking things. That's where their computer is, because you need so much computing power to do anything like artificial intelligence. You're certainly not going to fit it in there, and you're not going to fit it in this head of this creature here. That computer is going to be someplace else. The artificial intelligence is separate from the robot. Robot is just manipulators, driven by motors and pneumatics and so on. So if AI is your brain and robot is your body, and it's wonderful that we have the ability to walk around with our computers inside our heads, but that gives us some limitations as well. But once you understand this concept, then a robot can look like this, and you can call it a robot, or it can look like this, and you can call it an autonomous vehicle, right? And these are coming up. And maybe part of the intelligence is in the vehicle, but maybe some of it's out in the cloud and it's networked to the car, and maybe the cars are talking to each other so they know where each other are, and then you've got distributed intelligence, all right? But you've got to keep the device separate from the AI. Because you could even think of your home as an artificially intelligent robot. If you've got a device that can get on the network and you could say to it something like, Alexa, lock the doors, and all the doors lock, right? The robot is a house. And that actually exists, by the way. There are devices you can buy that you can talk to, and you can say dim the lights, play Bach, lock the doors. In fact, I have a thing called an Amazon Echo, and you can even say, Alexa, good night. And when you say, Alexa, good night, she turns off all the lights and locks all the doors. And then she says, good night, sleep well. Because it's got a female voice, right? If it had a baritone voice, we would call it he, and his name would be Alex. Okay, so how many kinds of artificial intelligence are there? There's a bunch. And they have different names, and they have different definitions, and these definitions actually do have meaning. So I'm going to explain what all those things are. And I was going to talk about, this is the part of the talk I had to cut out, this other stuff. Because people who are afraid of artificial intelligence attribute to artificial intelligence a lot of other attributes that have nothing to do with intelligence, or do they? Like consciousness. There's a big discussion going on amongst biologists and neuroscientists whether consciousness is an emergent quality of intelligence. Like, if you get intelligent enough, does consciousness just emerge as part of that? Or is there something else going on? So I did a lot of research on that, and I'm not going to tell you anything about it today. And then there's another level of consciousness, self-awareness. This means you're thinking. This means you're thinking about thinking, right? This is when you recognize that you are an individual who has thoughts, and there are other individuals who must be thinking too. And when you start doing things like that, then you do get scary, right? Because if you were an artificial intelligence and you had this, then you might start thinking about, why am I doing what I'm doing? I don't know if I want to wash the dishes tonight. Right? Maybe I'll rebel. So let's talk about the first kind of AI, and that's apparent AI. Apparent AI is where we do something that really looks intelligent, but it really isn't. It's just clever engineering. So an example of that is when they first started building nuclear power plants, they would put sensors all over the place, and the sensors would measure things like how fast is water flowing through a pipe, and how hot is the water getting, and so on. And if the water got hot enough where it passed the threshold, that would trigger a solenoid which closed a valve. And if you were a caveman and you were walking through the nuclear power plant, wondering how you got there, and you saw a light start to flash and a valve start to turn, you'd say, intelligence. There's an intelligent agent at work. No, what there was a very smart engineer who designed a system that captured his intelligence and then activated his intelligence when it was necessary. And we can do that in hardware. We've been doing it for a long time. A thermostat senses the temperature and turns your furnace on and turns your furnace off, and it's doing intelligent stuff, right? We also do it with software. A lot of people talk to their computers, and you wouldn't believe the things they say to their computers sometimes. But they're not really smart, right? They act smart, they do smart things, they do very useful things, but it's all just software. But here's the thing, they're not flexible at all. Microsoft comes out with an operating system and it's full of bugs, and you're praying for the day. Well, don't waste your time praying, but you're hoping for the day You're hoping for the day that Microsoft will come out with an upgrade. So they do. They come out with an upgrade. You say, oh, great, I'm going to install this, and it's going to fix all that bugs. And it does, but then it gives you a whole bunch of new bugs, and you start hoping again. So these things don't learn, right? That system that measures the temperature and turns on a valve, it doesn't learn. If you wanted to do something a little different, you got to go in and you have to manually do things. And we used to call these things expert systems. And IBM, a few years back, built this one. And gee, it's hard to see this, but this here is a door. So that's the size of a human. And all the rest of this is a machine they called Big Blue. And Big Blue was built as one of the first examples of artificial intelligence, and it was going to beat the world chess champion at chess. Now, if it could do that, that's artificial intelligence, right? Because of all the things humans do, intellectually challenging, playing chess has got to be up there. Well, it turns out it wasn't artificial intelligence at all. There was no artificial intelligence to it. It was just software. It was algorithms. And it was a really simple one, too. It was, if he does this, I'll do that, then he does this, and then I'll do that, and then he does this, and I'll do that, all the way to the end of the game. And I'll give that whole series of moves a score. And now I'll say, well, what if he doesn't do that, he does this instead? Then I'll do that, then he does this, and I'll do that, and he'll do this. And 10,000 iterations down to the end of the game, and I'll give that a score. Is this score better than the last score? If it is, then this is the move I'll make. And it did that for every possible move that Garry Kasparov could make, and every possible move that Big Blue could have made in response, and then it picks the one with the highest score, and that's the move it makes. It's a machine doing a mechanical thing. Is there intelligence there? Yes. The person that designed the algorithms was intelligent, and he captured his intelligence like a sculptor captures an image and carves it into stone, right? The programmer captured his intelligence and carved it into algorithms that the machine just repeats. It's just a machine. You're turning a crank, and sausage comes out the end.
Who won?
Sorry, what?
The chess match. Who won?
Who won? The machine won. But it wasn't smart. And the other thing about, well, I'll get into that. So here's another example of artificial intelligence. At least what they're saying is artificial intelligence today. This is a Nest thermostat. You can go out and buy this thermostat. It costs a lot of money. It costs like $200. And they say it's intelligent because it learns what you like the temperature to be depending on the day of the week and the time of the day. Okay? It doesn't really learn anything. It's got a memory chip in it. And if you go up to it at 2 o'clock in the afternoon on a Thursday and you set it to 68 degrees, it puts that in its memory. And when next Thursday comes around, it just plays it back. Right? So all it's doing is recording your activities and playing them back for you. The interesting thing about this, though, is it sure seems intelligent. And the reason it seems intelligent is because you're programming it. You don't know you're a programmer, but you are. And that's one of the big things that's happening today, is that we're all becoming programmers because the machines are getting better and better at understanding our actions as input. And that leads us to this thing. This is the thing I was talking about before, the Amazon Echo. This is a device, like many other devices, that you talk to, and then it does, in response to you talking to it, something beneficial to you. And I'll dig into that a little deeper in a bit. But apparent artificial intelligence, basically, it's a machine running on code that was written by somebody called an algorithm. Now, narrow artificial intelligence, that's the next level up. And this is the real deal. Narrow artificial intelligence is differentiated by the fact that it's taught or it learns a skill. So if you create something with narrow artificial intelligence, you don't have to come in and rewrite the software every time you want it to do something different. It can actually learn to do something different. And that's quite a concept. They're still task-oriented. In other words, if you teach it to do a thing, like if you teach it to write music that sounds like Mozart, that's all it can do. Now, you might be able to teach it to write music that also sounds like Bach, but it's kind of stuck in the world of you can teach it to write music, period. And there are some good reasons for that, which I'll dig into. But anyway, so an example of that is Watson. This was another IBM invention, and Watson was designed to play Jeopardy, another game. And it won, right? It beat the world champions at Jeopardy for a couple of reasons. So again, everybody threw their hands up and said, oh, artificial intelligence. Could you save it for the end?
Is this called machine learning, or is that separate?
Yeah, this is machine learning, yes. But actually, most of what Watson did was, it was a search engine. Most of Watson was a search engine. So when they would ask it a question, and the question was framed as an answer, and Watson had to figure out what the question was, it would formulate that question, and then it would just do a search, just like anything else. It would do a search. Big deal. But there was artificial intelligence in there, and I'll get to that in a second. The next thing that came out that was a big deal in the world of artificial intelligence was this thing, AlphaGo. This was Google. Google bought a company called DeepMind, and DeepMind was all about deep learning, machine learning, and they taught this machine how to play Go, and it beat the European Go champion 5 games out of 5, and then it beat the world Go champion 4 games out of 5. And it was taught to play Go, just like you would teach a person to play Go. Well, kind of. But real artificial intelligence of a narrow kind. All it can do is play Go. It's not going to take over the world. So narrow artificial intelligence, runs on something called a neural network. And I'm going to tell you exactly how that works, and this concept of deep learning. After that, the next level up would be artificial general intelligence, and this is also referred to as HLI, human level intelligence. And this is the big deal. And this is a picture of what it looks like today. We can't do this at all, but it implies a lot. It means, it's human level intelligence. It can reason. It can recognize that it has a problem without being told it has a problem, and then it can say, well, I've got to come up with a solution, right? Recognize that, and then formulate a solution, and then do scientific things like test it to see if it actually is a good solution, and so on. So, thinking abstractly and solving problems, and this is the big one, learning quickly. Why is it you can tell a little girl what a cat is a couple of times and she knows what a cat is, but when you tell a computer what a cat is, it says, tell me that again, 250,000 times before it gets it, right? And one of the reasons is because humans learn by using models. We build models in our heads of what the world is like, where computers don't have that capability today. So to get to this, a computer would have to be able to build a model of reality. And computers do not have that level of sophistication at this point in time. General AI doesn't run on anything. The next level of intelligence, which also doesn't run on anything except movies, is artificial superintelligence. And this is the one everybody's afraid of. This is the one everybody's really afraid of. And the reason they're afraid of it is not because they watched the Terminator movie. It's because a few people have written books about just how dangerous real artificial superintelligence could be. Because the premise is, eventually the machines are going to be smarter not just than each human on the planet, but smarter than every human on the planet put together. And when a machine becomes that smart, then we become, in its eyes, I use the word eyes loosely, we become nothing more than ants or rodents or paper clips or things that, why would it care about us? So this is the big subject of fear, but it could also be a good thing, right? There's this guy, he's a super intelligence, and everybody loves data. So, is it going to be the Terminator or is it going to be data? And we could talk that, that's the part of the talk I cut out, so wait till next time. But let's dive into the apparent AI thing a little deeper. I told you it runs in algorithms, and the algorithms are getting better, right? So we have algorithms that do things like pattern matching and regression analysis. So let me show you what an algorithm is, and I'll try to make this really quick. A woman is married to a programmer, and she says to her husband, "Dear, I want you to go to the store and buy a loaf of bread, and if eggs are on sale, buy a dozen." So he comes home with 12 loaves of bread. And she says, "Why did you do that?" And he says, "Because eggs were on sale." Because that's the way a programmer thinks. So let's write this out in code. She says, "Go to the store." Now, when you write an algorithm, you have to think about all of the parameters that are in there. What does store mean? What kind of store are we talking about? So you put in things called parameters that say, you know, this is the frame I want you to put it in. We're going to go to the grocery store. But what does it even mean, go to the store? Right? People when they talk to programmers, they're like people that talk to drummers. You know, it's like, oh, you beat a drum with a stick. Anybody could do that, right? Anybody can write code. Go to the store. Piece of cake. Well, what does it mean to go to the store? If you're a programmer, you have to think about this in a lot of terms. It's like, well, you want me to go to the store. What kind of store are we talking about? Is it a hardware store? If it's a hardware store, maybe I want to take my truck. And if I'm going to take my truck and go to the hardware store, where am I leaving from? If I'm going from home, well, I know how to get there and I know which store I'm going to go to. But what if I'm not at home? Then I have to figure out where I am and figure out where I want to get to, and then I'm going to have to figure out, you know, how do I drive there, and then I'm going to get in my vehicle and I'm going to start it. Well, do I want to check the gas before I take off, because I might have to make a detour to a gas station, and on and on and on. You have to think of every freaking detail. And if you get it wrong, you know, you wind up with 12 loaves of bread. So, and that gets us back to this. Why when you go to the store, what do you do when you get there? Well, you got to buy bread. What kind of bread? How much bread? Do you want loaves? Do you want pita bread? Do you want, you know, whatever they got? And then if it's on sale, if eggs are on sale, then get a dozen. Buy eggs, not 12 loaves of bread, right? And what kind of eggs and how much and so on, and then you get home. So that's what an algorithm looks like. And I'm going to show you the pattern matching algorithm now, because this is how computers learn to speak languages and translate. If you go to Google, you can give it a phrase in English and it'll give it back to you in whatever language you want. So if you want to know how to tell your wife to go to the store and buy some eggs in French, Google will show you how to do that. And it looks like artificial intelligence, but it's not. All it is pattern matching. This is a shot of a Chinese menu, and I tried to get one in Italian or French or something, but in Europe they don't do this. They don't do the Chinese and the language side by side, so I couldn't. But anyway, so here's a menu, and you want to teach a computer how to say chicken in Chinese. So one of the symbols over there, you know, means chicken. Well, which one? It's the one that appears every time the word chicken appears. You don't have to know what chicken means to figure out that this word matches this symbol. Because every time that word appears, that's when that symbol appears. And you can learn some other things too, like, I don't know what lo mein is, or what main is. I'll bet you it's noodles, but I'm not sure. But anyway, there's the symbol for it, right? Here's another one. Now that accompanies snow peas, black beans, and string beans. Now I'll bet you it means bean, right? And I'll bet you something else. The Chinese do not think peanuts are beans. But if you had enough examples of Chinese menus, you could figure out every Chinese character that represents a food item, including how it's cooked and what kind of sauce, and even if it's spicy or not, just by matching patterns, right? And there's no intelligence to it. All you have to do is write an algorithm that says if this pattern appears every time this word appears, they must mean the same thing. And then we can translate from English into Chinese. Okay, here's another thing that's important, and this is regression analysis. And this sounds really complicated. This is something I used to do for AT&T. I was actually it was NCR. I was a product manager for data analysis for massive amounts of data. And this concept was invented by American Airlines when they came up with their loyalty program. And they invented this idea. And the idea is this. We want to fill every seat on every plane, so we want to encourage people to fly with us. So how do you get people to fly with you? Well, you have to learn a lot about them. what makes them fly? How often do they fly? Why do they want to fly? And how do you collect that information? You give them a card with a number on it. And every time they fly, they have to use that card, and you record all the information you can. And you find out, are they Caucasians? Are they making over $100,000 a year? Do they smoke? You know, and just all those details. And you plug them into a formula that says, you know, is it a man or a woman? And what percentage of men fly versus what percentage of women fly? And you add that to the fact that they live on the East Coast in an industrialized city, and so on. And you can use that to apply to anything. So I looked up who votes for Hillary Clinton versus who votes for Bernie Sanders, and I plugged in my stats, and I ran them against this formula. So if you're a male and you live in the Northeast and you're a white over 45 and your income is over $50,000 a year and you're college educated and you're liberal, these are the percentages of those people that vote for Hillary Clinton versus Bernie Sanders. And when you do all the math, it says, I am 1.5 times more likely to vote for Hillary than I am to vote for Bernie. They got this wrong, by the way. But if I knew these data points about everybody in the room, I could come up with a pretty close estimate of who would win if we ran Hillary against Bernie in this room, right? But I would have to have all that data about you. How do I collect all that data? Where do I get that data from? And that's one of the things that's driving artificial intelligence, is now we have all of that data coming up. So how does artificial narrow intelligence work? Because you've seen this example of Siri and Cortana and Google Now and Alexa and all these devices you can talk to. And it seems like you're carrying around something in your pocket that's really smart. Only it's not. The artificial intelligence that's associated with this, and there is artificial intelligence here, only it's not here. It's up there somewhere. It's in the cloud somewhere. Somewhere in the network, there's a computer that's running artificial intelligence algorithms and is doing something for you. And there are lots of examples of this. I particularly like this one. It says, what can I help you with? I'm Siri. I know nothing about grammar. But what can I help you with? And these companies are spending huge amounts of money to capture a particular market, which is the artificial intelligence as a personal assistance market. This is how they're going to own you. They already have all of your data up in the cloud. And this includes television companies, right? Every time you watch something on cable TV, they know what you're watching. They're collecting all that data. And eventually they're going to use this data to make some money off of you somehow. This one is Google Now. I know it's hard to see. And this one is the one that's soon going to be in Facebook. They're putting an artificial intelligence engine inside Facebook. And that's the one a lot of people are scared of. And the thing that's driving these is this voice recognition capability. And there's Alexa again. And these are all interfaces into where the real artificial intelligence is, right? So it could be here. I can actually, and this is a cool thing, right? It's black until I hold it up like this. Come on, yeah. See, and then it lights up because it knows I'm looking at it. Oh. Isn't that cool? And I can say to it, okay, Google, what's the weather going to be tomorrow? And it'll actually look up the weather and show it to me on this little screen. Now, you know there's no brains in here. You can't even prove there's any brains in here. It's somewhere else. So these are all just devices that hook you into that. And here's how they work. You say to Alexa, Alexa, open quick events. And this device records your voice and sends your voice across the network, literally your voice, across the network up to a server in Amazon's cloud, which they call AWS. And then up there, there's a speech-to-text engine that converts what you said into text, as though you typed it in. And then it takes that typed information and sends it down to a server where the quick events application actually runs, right? So is there artificial intelligence here? Well, this is just running algorithms, and it's going to hook into my calendar, and it's going to, you know, set up an appointment for me on my Google Calendar and all of that stuff. The artificial intelligence is in that speech-to-text engine. When I say, set an appointment for Saturday at 3 p.m., I'm going to, whatever I say to it, and it has to figure out what I said. It's got to figure all that stuff out and make sense out of it. And then after that happens, then I get the response back, and there's going to be a text-to-speech conversion up here. That doesn't take any intelligence at all. Text-to-speech is really easy. And then it sends it back to the device, and the device talks to me. And it's like all the intelligence is there. The real artificial intelligence is that piece there. Everything else is dumb stuff. It's machines. So an example of how difficult it is to interpret English. A panda walks into a Chinese restaurant, and a waiter comes over and says, "What would you like?" And the panda says, "I would like some steamed bamboo shoots." The waiter goes to the kitchen, gets the steamed bamboo shoots, brings them out. The panda sits there, eats the steamed bamboo. And when he's done, he gets up, pulls out a gun, and kills the waiter. The owner of the restaurant runs out. "What the hell are you doing? You killed my waiter. How could you do this? Who are you?" And the panda says, "I'm a panda. Look it up." Well, after the ambulance comes and the police and all that, the head of the restaurant goes and he gets a dictionary and he looks up panda, and it says panda. Large bear, lives in China, bamboo forest, eats shoots and leaves. For a computer to understand what people say and make sense out of it is one of the most complicated problems there are. So how do you do something like that? Well, there's a guy named Ray Kurzweil. Somebody asked me if I read any of his books. He wrote a book called How to Build a Mind. And he says, here's how the brain works, and this is how I'm going to build smart computers. I'm going to build pieces of machinery that I call recognizers. And each of these recognizers is going to be programmed to recognize a thing. Now, this is going to be optical recognition. So I'm going to have a recognizer that recognizes a horizontal line. I'm going to have one that sees slanted lines going that way and one that sees slanted lines going that way. And then I'm going to have higher level recognizers, and they're all going to be cross-connected. And at the low level, if I have on my input side, say, the letter A, right, the low level recognizers are going to look at that A, and the ones that recognize a slanted line going this way, and a slanted line going this way, and a horizontal line, are all going to recognize that component. And when they recognize that component, they're going to send that information up to the next level recognizers. And this one says, if I get those three components, that makes a letter A, right? So now I've got a second level recognizer that recognizes a letter. And it came from a first level recognizer that recognizes a line. Well, maybe there's a set of recognizers at this level that are looking at pixels. And pixels in a given configuration might make up a line that's slanted in a direction or horizontal or vertical, right? So with a few different levels of recognizers, we got all the way from pixels, which are nothing more than dots, all the way to letters. And it only took us 3 steps to get there. So that's pretty cool. When the A lights up, we know we've got an A. What if we have something that's not quite an A? What happens then? Well, what you're going to get is percentages. So this thing says, I've got a good solid line here. So it says that's 100%. Right? This one, though, has a broken line. It says, well, I'm 75% sure that it's a line going like that. 75%. And this guy, because that's a really indistinct line, he said, well, I'm only 50% sure. So that should look a little bit familiar to you, because what that is regression analysis. It's that same formula that American Airlines invented to figure out whether you're going to fly first class or not, determining whether that's an A or not, compared to, well, maybe it's a V, right? Because there's a probability of 1.75, it's a V, versus a probability of 2.25 that it's an A. So, it's a question. If you want to fine-tune it, we add some more recognizers that look for things like maybe, an apex or the bottom of an angle. And then you get a better definition. And if you make enough of these different levels, right, you have something called a deep neural network. How deep is it? Well, this one is 1, 2, 3, 4, 5 levels deep. And how do you train this thing now to do something useful for you, like recognize letters on a page? And we build machines that do that. And we build machines that turn speech into text using this kind of thing. And now you know how it works. It's regression analysis, neural networks, recognizers, cross-connected. Interesting point for you. If a recognizer takes 100 neurons, a human brain in the cerebral cortex has about 23 billion neurons. Each one is cross-connected with anywhere from 10 to 100,000 other neurons. So the human brain, if it looks like this at all, is so much more powerful than any machine we could build. That is, again, beyond comprehension. The numbers become meaningless. But anyway, that's what we're doing. So when they build something and they want to do guided machine learning, there's two kinds of machine learning, guided and unguided. When you do guided machine learning, what you do is you take a bunch of pictures of cats, say, hundreds of thousands of pictures of cats, and you feed them into one of these neural networks, and you tell the neural network at this end, these are cats. And they do something called back propagation, and this is where the software comes in, where they push back this way. What you're looking at is a cat. That's the answer. So find me the network, tune all of these recognizers until we get cats out this end. Right? So you do that, and it builds all of that. It uses that back propagation, and it tunes all these recognizers until it matches cats. And then it loads that up, and then you feed it in a bunch of other pictures that are not cats, and you say, these are not cats, and now it knows the difference between cats and not cats. And literally, this takes hundreds and hundreds and hundreds of thousands of pictures of cats to do this, and they actually do exactly what I described. Now, companies like Google have no problem doing this because you want pictures of cats, they're on Google. You want examples of English, French, German, Italian, scientific papers, it's all out there, it's all accessible to Google. And when you sign up for a service like Facebook, and you hit the accept button, one of the things you're doing when you hit that accept button is you're saying all the information that you know about me, where I surf, what I read, how long I stay on a web page, you own all of that. And they do. And they're using it to train these networks to do various things. Unguided machine learning.
Ron, you just brought up a question that I wanted to ask, and that is, they own all our information. We give it to them sort of
Willingly,
or at least unknowingly. And I think there are lots of implications about that.
There are. Could we save it for the end, though?
Yeah, no, I'm just
Okay.
going to put it out there in case you want to.
So then there's unguided machine learning. Unguided machine learning works a lot the same way, except you don't have to actually do a lot of the steps that guided machine learning takes. In this case, this is how they taught the machine to play Go. They put in a whole bunch of actual games of Go that have been played by humans, and they fed it into the neural network. And all they told it was, figure out how to win this game. And of course, they had to codify that some way, right? What does it look like when you win a game? So they fed all that in, and it generates algorithms for gameplay. And again, it did the same thing. It did the back propagation and says, look for strategies for winning at Go, basically, and tunes all of those recognizers to do that. But then it does something that's really slick. It starts playing games against itself, and this is called reinforcement learning. And it does that to loop through the neural network and keep tuning it and tuning it and tuning it on its own, right? It's making up games, it's playing against itself, it's turning the chessboard around or the Go board and saying, okay, now I'm going to play the other side, okay, now I'm turning around, now I'm going to be this guy, right? And it just does that hundreds and hundreds of thousands of times, and at the end, it beats the world Go champion, 4 games out of 5. So that's unguided machine learning. And when they first started using this technique, they started with Atari. And on the input side, all they fed in was pixels, right? Because Atari to a computer is just a collection of pixels. and they gave it controls, and it got the score. And just looping around and around and around without any instruction, like we would understand it. If you sat a person down, you'd say, okay, this is a game. The purpose of the game is to move the paddle back and forth and bounce the ball up into these bricks and make the bricks explode and so on. They didn't do any of that with the machine. They just said, make the score go up. That's all they told it. Make the score go up. And it learned every Atari game, and it learned how to play them better than humans. It did it in a few hours. And it used what it learned in every game on the next game it played. So when it played Pong and it learned that moving the paddle this way would eventually connect with the ball, right? And the paddle hits the ball, and now it makes the ball do something. And if they hit the ball just right, they can make it go faster, they can make it go slower, they can change its direction and so on. And then the neural network would apply that to playing Breakout, because there's a paddle and a ball, right? So it transfers the learned skills from one game to another. So it's a little better than, just training something to recognize cats and nothing else. Now we can train something to play a game, and it can be pretty much game independent as long as, the inputs and the outputs are something that are repeatable and expected. Now, this was no small feat, though. And again, remember I said, anything that approaches artificial intelligence is not going to fit in the head of a robot. This is why. It took 170 graphical processing units to build this machine. And remember, each one of these is hundreds of computers that do nothing except parallel processing of some input. So this is like 500 times 200. That's 10 with 4 zeros after it, 100,000 computers, and 1,200 CPUs, all running in parallel, simultaneously, just to play the game of Go. And they had to build a narrow AI, a neural network, that did the strategy that says, okay, what am I going to move in order to capture the most territory on the board? But they had to build another neural network that said, well, if you do it that way, what is the probability that you're going to win the game as opposed to losing the game? And then they had to build a third neural network that says, well, we're playing against time. So while you guys are arguing about this, the clock is ticking, and it's time to stop going down those paths that you have low probabilities and go back up to a higher probability, and this is the move we're going to make, time's up, right? So very, very complex machine. It's actually 3 neural networks and lots of hardware to do that. And the amazing thing is, after we've taught this machine how to do it, it's been doing all this back propagation and fine-tuning itself by going round and round and round, playing games it's making up as it goes. We have no way of knowing what it did, right? It's on its own. It's like magic, and you can't get inside the magic box and find out what's going on. Because it would take us, if we did that, I mean, you could, but it would take us years to figure out, as human beings, what's going on inside that computer. Okay, next level of AI is artificial general intelligence. And remember I told you we don't do this today, but we'd like to. Well, here's the history of computers. I know this is really hard to read out there, and also it's a very misleading chart, and I'll try to tell you why it's misleading. But across the bottom we have dates, and across the side here, this is orders of magnitude of millions of instructions of computer operations per second. And it's orders of magnitude. This is not an arithmetic scale. It's a geometric scale. So it's 10 times 10 times 10 times 10 times 10 times 10 times 10 as we go up, right? Orders of magnitude. So this appears to be a straight line, but in actuality, it's a curve that's going like this, okay? And as the curve moves along, it's getting steeper and steeper and steeper in terms of computing power over time. Now, when you have a curve like that that does that, if you put it on a geometric scale, it looks like a straight line as long as everything is growing at that geometric rate. So it looks like it's a straight line, but notice these green lines here. What this is a projection. If we took these dots, and these are all different computers with different amounts of power at $1,000, okay? This is how many instructions can it do per $1,000. You know, they tend to cluster and they tend to form a line. And this line is if we took the projection of what was going on in 1965, okay? And this is what was going on in 1985, and this is what was going on in 1995. And you notice that it's getting steeper. So not only is it getting more and more powerful for $1,000, which you can do on a computer, it's accelerating. And this has implications. Eventually, the line goes vertical, right? And there's a term for this. It's called the singularity. When computer power goes vertical and just goes straight up, that's when we get to things like artificial superintelligence, because you know that's more smarts than you can shake a stick at. So how smart is smart? Well, if we look at what was going on back in 1997, that's when IBM built Deep Blue, and there's the dot for it, okay? That coincides with these three lines, and we can go across from there. We can look at Watson in 2011, and there's the dot for Watson, and that's when this graphic was made. So there's no dot on there for AlphaGo, but AlphaGo would be here. This is 2016, and it crosses those three lines. So how smart are these machines? Well, if you look at AlphaGo, if DeepMind is on this line, then it's somewhere between the computing capabilities, and I don't want to say intelligence, I don't want to say consciousness, it's computing capabilities of a lizard and a mouse. Well, what does that mean? Well, if the neural network that was used in AlphaGo did nothing but visual processing, it would have the ability to see things as well as a lizard or a mouse, somewhere in there. Now, you know, would it be able to catch flies with its tongue? Maybe. but if it did that, it wouldn't do visual processing too. They're two separate things. If we were on the next line up, it would be somewhere between the intelligence of a mouse and a monkey. And if we were on the third line up, it would be probably, you know, the computation capabilities of the brain of a monkey. That's pretty smart, right? The rhesus macaque monkey is one of the 10 animals in the world that is known to be self-aware. So we're getting close. We're somewhere in that range of, you know, how smart our machines are at this point in time. So we're getting up there. We're not as smart as a human, though, because a human, if you see up at the top there, it requires 10 to the 9th million processes per second. It has to do 10 to the 9th million. Well, 10 to the 9th million is 10 to the 15th operations per second. That's a 1 with 15 zeros after it. That's a lot. That's what's going on in your head right now. You didn't know you were working this hard, did you? So to get up to there, when is that going to happen? Well, if we project this line out, the 1965 line, it says we're going to get there to a human level intelligence in about 2045. So if we're on the slow path, 2045. If we're on the middle path, 2030. And if we're on the fast path, and remember Google came out with their Tensor chip, their synaptic processing unit. IBM came out with a synaptic processing unit. Everybody's building these things. We're probably on a fast path. We could reach human level intelligence in the 2020s, 2022, 2023. How far off is that? 6 years? 7 years? And you might think that that's ambitious, but consider this. 1985, we were a trillionth of the way there. 1995, we were 3 orders of magnitude closer. 20 years after that, 6 orders of magnitude closer. So every 10 years, we're getting 3 orders of magnitude closer. How many years will it take to go from 1,000th of the way there to there? 10 years. 2026. So everything we look at says, you know, we're getting there, we're getting close, it's imminent. Here's an example of IBM. They have a neurosynaptic computer chip, and they build it onto a board, and it's got 16 of these chips on the board, and each one of those chips is capable of doing 46 billion synaptic operations. Now, figure that to mean that those are recognizers, right? If we're talking about neural networks, we're talking about recognizers. So 16 times 46, that's 736 billion synaptic operations per second. That's 736 times 10 to the 9th. I'm sorry for the math. But don't forget, what we're trying to get up to is 10 to the 15th. And we're only up to 10 to the 9th. So we've got a ways to go. But we're getting close. And in fact, we're so close, Donald Knuth, who is a major operator in the artificial intelligence world, says AI has by now succeeded in doing essentially everything that requires thinking, but has failed to do most of what people and animals do without thinking. Like understanding what a cat is, right? Because you can't go up to a computer and say, you know, I was at a concert last night and I saw a woman play the piano, and I don't care how smart machines are, this woman could play the piano, all right? So, you know, as close as we're getting, we got a way to go. And the reason is human intelligence, the intelligence that we recognize as real intelligence, isn't just, you know, one kind of neuron repeated over and over and over again, running loops of software. We're a lot more than just neurons. But one of the things that people are thinking about doing and trying to do is say, well, one approach is let's re-engineer the brain. What we'll do is we'll freeze a brain, and you know, it doesn't have to be a human brain. We could just take a really smart mouse, right? We'll freeze a brain, and we'll slice it with a microtome, and we'll take pictures of every slice, and we'll figure out where every neuron is and what kind of neuron it is and what it's connected to, and then we'll build a machine that looks just like that, and we'll have something that is a mouse brain, right? So that's an approach, and we can actually do that, and we can match the architecture, the components, the connectivity, the organization, all of the things that make up a brain. Of course, capturing the software that's another issue. And we can do that today. We can emulate the brain of a flatworm, which has 392 neurons in its head. That's not very impressive, is it? 392 neurons? That's the best we can do? Yeah, that's the best we can do. Now, a human brain has a lot more neurons than that. It's got 100 billion, a quarter of which are in the neocortex. But they say, given the technology we have, we might be able to do that as early as 2030. Well, we're going to have smarter machines than people around that time anyway. Do we have to mimic the human brain? And is there an advantage to doing that? Maybe there's a disadvantage to that. Because you know what people are really afraid of with superintelligence is we're going to build a machine that's not only as smart as we are, but just as screwed up in the head as we are. Right? Like, you sure you want to mimic a human brain? That might be a big mistake. The other option is we can just let brains evolve, let computers evolve the way they've been evolving, and let the invisible hand of the market drive what they do. You know, if our autonomous cars are successful, you're going to see lots of money pouring into research and development on what it takes to do an autonomous car. And it takes a lot. You know, they have to know how to get from here to there, and they have to know what the side of the road looks like compared to the middle of the road, compared to the line that's down the middle of the road. And you know, what does it mean when a ball bounces out into the street in front of a car? You know, and how do you teach a machine how to do that? So if autonomous cars take off, you're going to see a lot of R&D go in that direction. And if they fail, then all the money's going to go into something else, development of military robots or something like that. Another way to approach this is use something called genetic algorithms. I'll show you how they work in a bit. And you know, we'll just keep iterating the processes we're doing today to get there. Or we can use the machines themselves that we're building and teach them using deep learning technology how to design computers and have them help us design the next level of computer, which will be smarter than the one we're using to do that. and then take that smarter one and have it help us develop the next smarter one and keep going that way. And what's actually happening is all of those things. And eventually we're going to get to something called artificial superintelligence. And when I started out in the computer business way back in the 70s, I worked at a company where we would use our current machine, which was called at the time the 732, to design the next level machine, which we called the 832. And we emulated it in software, and we ran it in test mode as a simulation to see, A, would it work, how fast would it run, how much memory would it have to address in order to operate, what would we have to change in the operating system to make it function. We emulated the whole thing, and of course it ran really slow, but we knew that when we built the first prototype, it was going to work. Well, if you keep doing that, and the machines keep getting smarter, we're going to get to intelligent, human-level intelligent machines in 15 to 20 years. And this isn't me saying this is all the computer scientists involved in doing it. And those machines are going to have a big advantage over us, because the human brain only runs at 200 hertz. That's 200 cycles per second. Our brains run really, really slow. It's a good thing we have 24 billion neurons working on the problem, because even though they're slow, we're making it up by having lots of it, right? But a computer runs at 2 gigahertz, and that's a 10 million to 1 ratio, and that's current technology. Also, computers have something we don't have, and that's connectivity to the cloud. So how much storage you have in your head is really limited by the size of your skull. And the size of your skull is limited by the size of the birth canal. So we're at an impasse here. There's nothing we can do about that. You know? But a computer can connect to the network, and storage is out there. And, you know, it's cheap. And it's getting cheaper every day. I used to work for a company that did nothing but storage. We were really interested in how fast storage was growing, because that's what we sold. And we were the most successful company in the world for a time there, because this was really taken off. And it's because computers can go out there and just grab all the storage they need. They can network with the storage. They can network with each other, which means if a computer in a factory that builds automobile components learns something, it can transmit what it learns to every other computer of the same manufacturer in every other car manufacturing facility in the world, and upgrade them all simultaneously and very quickly, right? For humans, that's a real problem. You got to go to school, and you got to pay attention, and you know, you got hormones raging, and you know, it's tough. Where computers learn very, very quickly, and they can update themselves, and they can upgrade themselves. So they're going to get lots smarter. So let's talk about how smart is smart. In terms of orders of magnitude. Here's the smartest dog in the world. His name is Chaser. He can identify 1,000 toys by name. You can say, Chaser, go get the yellow octopus. And he will run into the next room, find the yellow octopus, and bring it back to you. And he's got over 1,000 toys, and he knows their names. And he can generalize. If you throw out a yellow ball and you say, Chaser, get the yellow ball, he'll bring it back. And you throw out a blue ball and you say, Chaser, get the blue ball, and he'll bring it back. And if you throw out another ball, and he's never seen before, and it's green, and you say, Chaser, get the green ball, Chaser will actually figure out, well, it ain't the yellow one, it ain't the blue one, it must be the third one, and he'll bring that one back. Really smart dog. I've seen him do his thing. He's got 160 million neurons in the cerebral cortex. So this is a mouse, 4 million neurons in the cerebral cortex. Here's a rat, 15 million neurons in the cerebral cortex. Here's Chaser, 160 million neurons in the cerebral cortex. So he's a hell of a lot smarter than a mouse or a rat, right? Well, here's Natasha. She's the smartest chimpanzee in the world. Natasha will take a drink of water, and she'll wave at you, and she'll do this. And you go over and you say, what is it, Natasha? And she spits right in your face. And then she laughs, right? So she's really smart. She's clever. When they first started working with Natasha, they put her in a cage, and she figured out how to unlock her cage. So then they put her in a pen with an electric fence, and she figured out if she took a stick that was wet and threw it against the cage, she could tell when the power was on and when the power was off, and then she started escaping from that. Really smart. She understands quantities. When they were testing Natasha for different capabilities, they would reward her. And she would check to see if she was getting as much of a reward as the other monkeys. And if she didn't, she'd stop cooperating. So really smart. 6.2 billion neurons in the cerebral cortex. Here's Chase. All right. Chaser was a really smart dog. Here's Natasha. And here's Stephen Hawking. Stephen Hawking, he's probably the smartest man in the world. His IQ is estimated to be somewhere around 200. 200. Theoretical physicist, cosmologist, predicted that black holes emit Hawking radiation. This is something, right? He wrote his first doctorate called Black Holes Aren't Hairy, something like that. Yeah, Hawking radiation. They named it after him. He's one of the people that's really concerned about artificial superintelligence. He's scared to death of it. He says this could be the end of mankind, artificial superintelligence, and he's the smartest man in the world. He's got 23 billion neurons in the cerebral cortex. So all the way down here. Here's Chaser. Here's Natasha. Here's Stephen Hawking. And this is drawn to scale. So how smart is smart? What does superintelligence actually mean? This is the bell curve for intelligence, and it's based on IQ, and IQ is your mental age divided by your chronological age, so the average is 100. And have you ever met anybody with an IQ of 100? I'm not going to be judgmental. But here's George Bush. His IQ was estimated to be around 125. And you thought he was an idiot, right? No, he's actually a pretty smart guy. 125, he's no slouch. He's not Mensa material. That's over 130. So, smart guy, not a genius. This guy's a genius. His IQ is estimated to be somewhere over 140. All right, so he is Mensa material. He's up there. And then you get to somebody who's really, really smart. And that's Einstein. His IQ was estimated to be somewhere around 200. And up at that range, for humans, 200 is almost meaningless. It's like, what does that even mean? You know, that you can sit there and visualize relativity and what happens with light when it's traveling at this speed of 186,000 miles a second, and there's a light beam coming from the other direction, and you know, and if you're driving a car that fast and you turn on the lights, what happens? You know, it's like, he thought about those things, and he's been right, dead on right, for 100 years. That's unbelievably smart. But what if you built a machine, though, that had an IQ of 300? What would that be like? What would it mean if you had a machine that smart? Well, we're going to find out, because it's expected, and this again, the expert predictions, the median expert prediction is artificial general intelligence, human level intelligence, somewhere around 2040, if not sooner, right? And the median expert prediction for artificial superintelligence comes 20 years later, 2060. So those of you who are young enough to live that long are going to find out just what that means to have an IQ that high. And this is the book. And Irma, I should have told you about this book when you asked me. This is the one. Irma asked me for a recommendation for a scientific book that was a lot like Frankenstein. And this is it. This is it. Nick Bostrom wrote this book 2013. And in it, he says, you know, artificial and superintelligence, be afraid, be very afraid. And he predicted all these dire outcomes. If we keep following the path we're going and we're not really, really careful, and artificial superintelligence is just as devious and nasty as humans, you know, we're in for it. And some people read that book who got really scared, and these are not idiots. Elon Musk read that book, and he says, holy crap, we better be afraid. And he put a lot of money behind his opinion. He started a foundation to democratize artificial intelligence so that if and when we will be ready for it, and it won't sneak up on us. And Stephen Hawking is afraid of it, and Bill Gates was afraid of it. Now, there's some other guys that aren't. Neil Tyson, I love his response to the whole controversy. They asked Neil Tyson, you know, aren't you afraid of superintelligence? He says, hell no, I'll just unplug the machine. Which is a great attitude. I like that. And Ray Kurzweil's not afraid of it either. He says, well, hey, What's going to happen is we're going to plug that machine into our heads and we're all going to become super intelligent. What's wrong with that? And that's let's hope it goes that way, right? Because it can go one of two ways. Things have always been kind of here. But soon, things are going to go all the way to extinction, or they're going to go all the way to we're going to live forever, happily ever after. And it's going to be one or the other, and whichever one it is, it's a permanent situation. Right? So, should you be afraid or shouldn't you be afraid? Well, that was part of the talk I cut out. So anyway, where are we today? Today we're in the era of, and it's shocking to me that they don't talk about this stuff on the news. You know, it blows me away that we have to talk about tweets on the news, when what's really happening today is we're in the era of cooperative AI. When they came out with Deep Blue and it beat Kasparov at chess, a lot of people said, well, now people are going to stop playing chess. What's the point? You know, the computer's going to win. You know, what's the point? Well, people did keep playing chess, and in fact, what they did was they started using chess computers while they were playing chess. And what we learned from that was that a person playing with a chess computer is not only better at playing chess than just a person, he's also better at chess than just the computer. A person with a computer, cooperative AI, is better at playing chess than either a person or a computer. So what's happening with Watson, one of the things they're doing with Watson now, and remember, Watson is just a really smart search engine, right? It's not even artificial intelligence, although they're starting to layer that in as well. But it's at Sloan Kettering, and they're doing cancer research, and it's working in cooperation with doctors. And what Watson can do is, it can get up to date instantly on every medical history that's available to it, every medical journal that's been written up to this point in time, every textbook that's ever been written on the topic, all the drug interactions, and they're discovering them constantly on an ongoing basis, all the research papers that are being written by people getting their doctorates in cancer research, all the experience and correlations that can possibly be made with all this information, and it can look at your genome too and see if that's a factor. So it can do a very targeted analysis of what your specific problem is, and based on your history and the drugs you've been taking and your ethnic background, it can prescribe a very specialized treatment just for you. No time in the history of humanity has this been possible until now. So cooperative AI is a very, very powerful thing. It's also got a downside. They've also come out with a Watson version of law firm. So if you're a lawyer, your days may be... So here's another example of cooperative AI. At Tufts University, they said, well, we've had a problem we've been thinking about for 120 years, which is, if you cut a flatworm in half, if you cut a nematode in half, not a nematode, a planaria, if you cut one of these things in half, it regrows both parts that are missing. The tail grows a new head, the head grows a new tail. How does it do that? Right? What does it take to make that happen? And for 120 years, they've been trying to figure out how the genes in that thing control the shape of the part that grows back. Why does it grow back two heads? Why just one? How does it know where it belongs and all the components go? And how come we've cut off my head, it doesn't grow back, you know? So they looked at that problem and they used what I referred to earlier as a genetic algorithm. And this has nothing to do with genetics. It's just the name of the algorithm. And I'll show you how it works. They take this artificial intelligence engine and they input all the data from all the studies that have been happening for the past 120 years on how planaria regrow a new part. And they took that data and they said, okay, create a gene model for a planaria. Now they had a lot of stuff to begin with, but there were a lot of parts missing, right? Because they're, you know, genes are very complicated and they don't know what genes do what and so on. So they created a gene model, and then they take the gene model and they run it and say, okay, what would happen if this gene model was right? What would it produce as a result? And how does that compare with what's actually happened? Was it a match? And then the answer is no. So then they take the gene model that came closest, though, and they modify that one and make multiple iterations of that one. And they run it again. And they say, okay, simulate this. And how does the simulation compare with reality? And is that a match? And the answer is no, but we're getting better. So they take the best one of those three, and they say, okay, now let's tweak that one 3 times and run it again. And you see what's happening here is they're mimicking natural selection.
Yeah.
That's why it's called the genetic algorithm. And they keep going round and round and round until they get to a perfect match. And when they get the perfect match, they say, okay, we're done. So the model, the algorithm knows when it's done. So they could just start it up and say, okay, run until you're done. And that's what they did. And it ran for 3 days. And at the end of 3 days, it came up with 3 known molecules and 2 proteins that were previously unknown. It figured out there were 2 proteins missing from all the information that it had, and this is what those proteins did, right? So it came up with that information. And it was the most comprehensive model of Flannery regeneration found to date. That's Michael Levin, he ran the project. And the model it found was not hopelessly tangled. It was actually a simple model that people can readily comprehend. Now, for 120 years, we couldn't figure it out. The machine figured it out in 3 days, and we understand it. The machine was right. This is cooperative AI, and I think it's a wonderful thing. And he goes on to say, this suggests to me that artificial intelligence can help with every aspect of science, not only data mining, but also inference of meaning of the data. Inference of meaning of the data. We're getting close to human-level intelligence, not on its own, but with the cooperation of people who understand what we're driving for, what are the implications of what we're looking at, and so on. Here's another great example. This is a machine that costs $5,000. It's programmed with a neural network to recognize malaria on a microscopic slide. So if you live in the middle of Zambia in a village and you think maybe there's malaria in your village, you can connect with the CDC on your cell phone, right? Because they all have cell phones in Africa. That's the big way of communicating. And you call the CDC and you say, I think we have malaria here. And they package up one of these $5,000 machines. They ship it to you. You take a pin and you get a drop of blood. You smear it on a slide. You put it in the machine and it says, you do not have malaria. Done. And if it says you do have malaria, you call the CDC and say, hey, I got malaria. You say, okay, we'll send the doctor. Right? Something that we could never do before. Here's one that some people find scary. This is pre-crime. They made a movie about this. This is where they take a crime map and they feed into it crime data, what crimes were committed where, when were they committed, where are the subway entrances, where are the bars, where are the parks, where are the churches, where are the schools, who lives where, what is their ethnic background, how much money did they make, did they go to school, and they run learning algorithms against it to see if there's any correlation with things like the weather, with phases of the moon and all that stuff, and then they show you on the map, this is where we expect crimes to happen today, so this is where you want to send your police so the crimes are prevented. There are 5 very large companies selling this technology right now to every police operation in the country. And some might call that profiling, right? Here's something else that might scare you. This is the British Navy. They come up with a machine called the Artful. We used to call it a submarine. But it's got an artificial intelligence engine on board, which is connected to 13,000 hydrophones. And the way it works is this. You're the captain of this ship, and you see a blip on the radar. And you go to the command control system, and you say, identify that blip. And then it uses the artificial intelligence engine and all the sensors, and it comes back and says, that blip appears to be a Russian cruiser. And then the captain says, okay, target the cruiser. And it starts tracking the cruiser. And while it's tracking it, it's calculating how to kill it with what weapons, fired in what direction, given the wind, the current, and yada, yada, yada. And if the captain says, okay, kill it, it's killed, right? Unless, of course, it's got a computer on it doing the same thing back, and then you get into a tussle. And I read it, after I put this together, I read another article where the U.S. Navy is doing exactly the same thing. The title of the article was, U.S. Navy builds Skynet. Okay, that doesn't scare you, nothing will. But I couldn't get any more data than that. That was one of those articles that teases you without telling you anything. So what's going to happen in the next 10 years with artificial intelligence? Well, it could be pretty terrific. There's a lot of talk about assisted learning in education, and you know, my son's an educator, and he hates screen time for kids, but it's the up-and-coming thing. And they're using robots to teach autistic kids now, and the robots can make expressions and stuff, and the autistic kids are not afraid of them as they would be humans. So they're making a lot of progress in a lot of areas in that. They're also predicting the elimination, I love the way this is phrased, the elimination of the boring parts of white-collar work, like research, logistics, negotiation. You know, and to me, that's fun stuff.
Yeah.
But if they eliminate enough of the boring parts, you may be out of a job, too.
Yeah.
And right now, you can go online and you can get personal assistance in a lot of areas. As an experiment, I put $3,000 into an investment company that uses artificial intelligence to pick stocks. And it's doing pretty well. And it only charges 0.25% interest. Well, my broker charges 2.5%. And he's given me a really good deal from what he tells me. But, you know, so he would have to make a lot more money for me than this thing. And it's doing pretty darn good. So, you know, eventually, if you're a stockbroker, you should probably start to worry. Because things are getting really powerful. But, you know, a lot of areas. Like, you know, think of the things you do today that you never thought to do. Like, if you're going to buy something, you know 50% of purchases are made on a cell phone in a store? Because what you do is you go in the store and you see that mixer that you always wanted, and it's $219, and you look it up, and oh, I can get it on Amazon for $200 and free shipping because I'm on Amazon Prime. And they buy it in the store. 50% of purchases are now made that way. What else does apply? Well, you know, we already talked about the information singularity. That's definitely coming. They're also predicting an economic singularity, and I got a presentation on that one. The economic singularity is when we get to the point where unemployment has reached unsupportable levels. And the prediction is today, that within 20 to 30 years, unemployment will be at least 47% in the U.S. 47%. At the height of the Great Depression, it was 25. So 47%, that should make you wonder, what are we going to do about that? Well, it could mean that we're going to enter a golden age. Because we're going to have, at that point in time, we're going to have all the benefits of a slave-based economy, but without the slaves. Right? If you think back to the golden age of Greece, the golden age of Rome, what was going on then? There was a huge slave population doing all the work. And if you were a citizen, though, you were a statesman, you were a public speaker, you had to know mathematics, you had to know astronomy, you had to serve in the military as an officer, of course, because the people that went out and got killed were the slaves. So we're going to have the benefits of that. Inexpensive labor, relatively free goods, almost free, because 3D printers, I mean, you wouldn't believe what's going on with 3D printers. I saw an article yesterday. There's a company building houses with a truck-sized 3D printer. So you want a house, they drive the truck in and they print you a house, and then they drive away. Pretty cool. So we're going to have extensive leisure time. So you get to catch up on your reading, eh? But, you know, free education, that's definitely coming. You can do it right now. If you don't care about the degree, you can get the best education in the world for nothing on the internet now. So we could be headed for a new renaissance. This could be terrific, or it could be a new terrible, terrible dark age, because there are things that we have to concern ourselves about, like autonomous warfare. When you've got machines that can fight machines, and the only involvement of a human is kill it, you know, and duck, then, you know, what does warfare even mean when it's machines destroying machines, and it's a war of attrition of machines destroying machines? What does that even mean, you know? Whoever has the most money and the best machines is going to own the world, or could. And if it's the wrong guy that gets that, like, you know, North Korea, that could be very bad. We could be concerned about super terrorism, because between what we can do with biology today, and if you saw my talk in February, you know, there's that. And then artificial intelligence added to that, you could have some terroristic scenarios that are just mind-boggling. And then who gets all the money, right? As most of the population loses their ability to make a living because of artificial intelligence and robots, the people that control the artificial intelligence and the robots, they're going to get the wealth. It's all going to rise to those people, and it's happening right now. You know, when you see Donald Trump blaming the Mexicans for the fact that we're losing jobs, that is such nonsense. We've lost 7 million jobs to robots in factories in this country. 7 million jobs to robots building cars. Those jobs didn't go to Mexico, and they didn't go to Mexicans. They went to robots. Because a robot, you can buy a robot today for $25,000 that works 24/7. You can't find a human that'll do that. Not for $25,000, right? So, you know, that's where the jobs are going. And then the last thing to be concerned about is totalitarian control. Given the technologies that we have today, if North Korea's dictator decided to maintain totalitarian control over his country forever as a dynasty, he can do it. Because the people can't wrest that away from him if he's got that kind of power. So, you know, should we be afraid or should we be hopeful? Yeah. Okay, and with that, we can go to questions. So,